So I recently heard about a different kind of voting system called ranked choice voting. So I actually saw this idea from this video called Simulating Alternate Voting Systems. You can just search this on YouTube. This is from Primer. It was a really good video and definitely does explain pretty well what some pros and cons of basically all these different systems are. And also there are some links in the description to some really cool interactive simulations as well. So I just wanted to see what it was like to just do it myself, as well as kind of look at some statistics as well. So we're going to go into this. First, I want to check out plurality voting and just kind of go through the steps on that. And then I'll go into the ranked choice voting. Okay, so here's what we're going to first need for the plurality voting. The way this works is to just take the candidate with the most votes and say they're the winner. But you kind of have to figure out, well, how do we simulate that? What we're going to want to do is create voters or just people in general. What we'll do is make a data set where each row is essentially a person, and then have each column be one topic or dimension to that person. And so we'll have to also figure out a way to match the voter to the candidate that they want. So in order to generate a random person, I'm going to want to establish some like randomness. And so I'm going to use a NumPy package for this. And here I'm just going to import NumPy as NP. I'm going to call np.random.seed with 1, 2, 3, 4, 5 as a seed. This is just allow for some reproducibility. That way, if you're following along at home, you get the same pseudo random numbers that I am. So I'll also be using pandas as a library. This allows us to basically easily store tables in a data set and then also do some data manipulation. So it's a really useful tool, especially in data science. So that's what I'll be using as well. All right, so let's generate 5 random people with 3 dimensions or topics and then put that into a table. So first I want to use np.random.random, and I'm going to give it the shape 5, 3, 5 people with 3 dimensions. So it looks like that. And then what I'll do is I'll use pandas to basically put that into a table, which looks a little bit nicer and it allows us to do some data manipulation as well. So I'll call pd.dataframe, pop our 5 people in there. So it looks something like this. So I know that right now that does not look like much of anything. How is that a person? I want to make it a little bit more familiar. And so I'll just quickly create a function that generates a random name basically. Okay, so here is my random name generator. Not the best, but it'll work. For our purposes here, I've established 2 variables here called consonants and vowels using English letters as a list. And then I have my definition for the function. And it starts out, I basically want it to be like a recursive call, but I didn't want it to go too long. So I have this like base case here. You will have this variable called I. It's set to default at 0, but if it goes beyond 3, then we just return basically an empty string just so it stops the recursive call. Other than that, though, it will establish a single consonant taken randomly from the consonants list using np random choice, which is just a way of choosing a random item from a list. And same thing with the vowel. And so all this random name is doing is just taking a consonant and a vowel and just concatenating them. But I want to have a variable length, and so what I do is set a check to see if a random check to see if this value from the random call, which I show you is just a decimal between 0 and 1. And so if that value randomly is less than 0.35, then I will simply return the constant and the value together, and that's it. So it's possible for this to just return just 2 letters. Or 65% of the time, it's going to return those 2 letters plus another call to itself with the I value incremented by 1. And I can keep calling it any number of times to see, just to get some random names. That's all. Okay, so what I want to do now is just give each person a unique name in our table. So to keep in mind, our people table is this thing. Pandas has some useful functionality though, so you can actually see the shape of this, or the size, the dimensions, by using shape, and it gives you a tuple 5, 3, 5 rows, 3 columns. That's all it means. So if I want to get the number of rows, I can just pull out that first value. And so that's all I'm really doing with this code here. We can actually set the index. So if we look at the index for this, that's it's called the range index, but basically it's just the value 0 up to but not including 5, and that's why we see on the left here 0, 1, 2, 3, 4 not including 5, and that's the index right now. What we want to do is just reset that to some random name basically. So what I've done here is I've used some Lisp comprehension to create a random name for each value in this range from 0 to 5 effectively, and that will give us the new index as a random name for each person. So if I run this code and I look at the new people table, you'll see that now we have random names. We have Moo, we have Yigi, whatever we want basically. So this allows us to see a row that is not just a number now, it's actual like kind of like a person. That's the idea. Okay, so what about the columns or the dimensions? These are just going to represent topics that a person is aligned on. And as this example will go, I just want to kind of use different kinds of numbers for this, but for the most part, it always has to be a number in the end, because we need to do math with it, all this stuff. So I'm going to make the first column to be how much a person loves a cat as a percentage. So again, 0% means they hate cats, 100% they love it, everything in between, of course. I want the second column to represent whether or not the person wants to lower taxes. So this is just a binary 0 or 1, 0 for no, 1 meaning yes. And I want the third column to be that person's income. For this one, we want to make a number that's, you know, obviously larger than 1, but we also want to make sure that the kind of distribution we're pulling from is not quite normal, because income truly, if you look at the data, income is basically never normal. We'll get into that a little later. But let's first rename our columns accordingly. So what I'm doing here is I'm doing what I kind of did up here when I reset the index. The index is like the left-hand side, the rows. The columns, dot columns, is just referring to the column names. So what I have here is now a list that I'm hard coding to these 3 values, and I'm just establishing that as a variable and then resetting people.columns to that. And then we can look at our people's table now, and we see that it has now been changed. Okay, so the first thing to note is the love of cats as a percentage is actually fine as is. Assuming a normal distribution, I think it's fine to do that. So I'm not really going to touch that column. The lower taxes does need a little revision because we're going to change it into a binary form, so it's 0 or 1. All I have to do though is just flip anything that's below 0.5 to 0 and everything that's above 0.5 to a 1. That's all I'm doing. So what I have here is using pandas functionality. There's a method called map.map, which takes a function and then basically maps it across each value within that series or list, basically. So if I look at the people and I index lower taxes, so people is a table right now, it's a pandas data frame. But if you do the square bracket and you say lower taxes, calling the name of this column, then it will just spit out that column all by itself. And we can actually change that as well just by overriding it. So if I do .map and I provide a lambda, if that value is less than 0.5, I want to return a 0. If it's less than 0.5, else return a 1. So if I run that, you can see now that we would get this value. Now, by default, the map function does not actually do any in-place changes. So I will want to overwrite this variable. This is all the same code as above. I'm now going to store it as a variable and then reset that value. And if we look at our people table now, we will see that it has actually permanently changed, and lower taxes now has 0 and 1 values for that. So the income value looks really weird as a number between 0 and 1, but honestly, I don't think I want to pull from a normal distribution. I want it to be from some kind of skewed distribution, like a beta or gamma or Poisson or any one of those. I'm going to go with gamma just because it's easy for now, but you really could kind of pick your poison on that. So I just wanted to quickly demonstrate what's going on with this gamma distribution thing and kind of why it makes sense. So here I'm importing 2 packages. One is Seaborn, the other is matplotlib as PLT. These are just some graphing libraries that I'll be using. And what I'll be doing here is using np.random.gamma. It's basically a way of pulling from the gamma distribution given these 2 parameters. I believe this is k and theta, if I'm correct. And that's just like basically determining the shape of the gamma distribution and size of 1,000. So I'm pulling 1,000 values from that. So for each value in this, I believe it's a NumPy array of random numbers from the gamma distribution. For each value, I'm just going to multiply that value by 25,000. I just did a little testing to kind of tease out what that number would be to make sense. Then I'm just converting it to an integer so I can kind of chop off the decimal. So this is going to be 1,000 numbers from the gamma distribution, and that will be our income values. Here I'm just setting some titles for my graph and then doing a Seaborn his plot with that with those values. So what we see here is basically the shape of our a gamma distribution that we could be pulling from, and you'll see here that it's skewed, which is kind of what income will look like. So income tends to be skewed in this way, where a value that's large tends to be like extremely large. One thing to note is income can't be negative, so it kind of worked out that none of these values were like negative. Okay, so here I have essentially the same code as above and here, except the only thing different is the size. I'm using the size that I'm pulling from the people table. Essentially it's just 5 people, but I like to keep things abstract. So this is going to give us a list of new income values that are from the gamma distribution, and I'm overriding that column called people with income. And if we look at our new table, when we overwrite it, we see everything's good and the income looks pretty different now. So let's put this all together. I want to be able to just call a function that just creates a bunch of people randomly for me, and that's kind of what this is. So I'm going to be using essentially all the code that I have from above, just putting it into one big function. I have established some column names that are hard-coded. I've established a random generated people here. I'm using n because I don't know how many people. This function will take n as an integer value. So I might have 10 people or 100 people, whatever it is. It will create that many people and as a people table. And then here I'm just going to add a bunch of random names using my random name generator. And then I'm going to be setting the column names as well as my modifications to the lower taxes column and the income column as well. And then it will just return that table. So let's run this. Let's create 10 people here. And we can see, well, a bunch of random names and all these numbers look good. So this is how we're going to generate both the candidates as well as the voters. Okay, so let's generate 5 candidates and 100 voters using our new function. All right, so I just ran that, and let's check out candidates. See those? Oh, look at that. Okay, so we have Yo. Okay, that's a good name. We also have Nizive. These are awesome names, and they look like they have some ridiculous income for our candidates. My goodness, given certain trends in how voting has been in the last few years, in at least in America, this may not be that weird. So how the heck do we say which candidate our voters want? And it has to be for each voter, right? So we need some way of ranking for each voter which candidate they want. So how do we determine how to do this? I think the way I would do this intuitively is that each voter will pick the candidate who is closest to them and I guess most relatable. That's, you know, how I would assume it goes. So this is a simulation, not necessarily the most realistic, but I think that kind of makes sense. And the way you can compare one row of our data to another person or another row of the data is to do something called pairwise distances. There's also cosine similarity. I'm going to go with sklearn's out of the box implementation of pairwise distance, but for the most part what we're going to be doing is looking at the row of data, which is just a bunch of numbers really, and comparing it to another row of data, which is just a bunch of numbers, and just seeing how close one set of numbers is to another. That's basically all this is going to be doing. So what I'm doing is I'm going to import from sklearn metrics pairwise distances, as well as from pre-processing I'm going to import min-max scalar, and I'm going to explain a little bit why we want to do the scaling. So one thing to keep in mind is our data has to all be numbers. We have to do math to this stuff, so we need it all to be numbers. And unfortunately, some of our data, like our income for example, have very different scales compared to the others. And if we have variables that are on different scales, that's going to be really hard to compare. So for example, if we have the cat loving percentage as a number, the difference between a 0 and 1 is drastic. But if you have something like income, the difference between 0 and 1 is actually not that much. So we need to make sure that our numbers are on the same scale, and that's why we want to use a scalar to do that. It allows us to compare between these different features or dimensions by looking at them all on the same scale. So what I have here is one way of doing that. It's called the min-max scalar. There are all kinds of ways of scaling. For this one, the min-max scalar just looks at a set of data and it finds the min and max and basically assumes that to be essentially the 0 as the min and the 1 is the max, and it scales everything in between to be on that scale. And so what I'll be using here is the candidates as the kind of starting point, and then I'll be transforming the voters based on that. So we're assuming the candidates are like the reference point. Doesn't really matter which one you use, just be consistent. Okay, so here I'm instantiating the scalar object, and then I'm fitting the object. When we fit the object, in this case the scalar, all it's really doing is doing what it needs to figure out, and that's really just the min and the max. And then once you have that, you can then transform any new set of data, and again it has to have like the same shape, so like the 3 columns, that's what it needs. I'm going to set that new transformed data to normalized candidates, and I'll show you what that looks like. So if we look at our candidates, they have not changed. So the candidates, even though we set dot transform, it's not going to do anything in place. It just keeps it as is, and then it transforms it and creates a new variable called that I'm calling normed candidates, which are normalized. And you can see it doesn't have the same pretty pandas table that we saw before here, but you can keep in mind that everything here is now scaled in the same way. So if we look at this value here, this is the lowest value in this column. That is essentially now the 0, and the highest value in the column in this one is now a 1, and everything is scaled relative to that in between. Same thing for the income. Okay, so now that we have our normalized candidates, we can actually compare our candidates to other candidates. What I'm going to do here is just to showcase what pairwise distances is actually doing, and I'm just going to pop in the normal candidates. Again, it has to be scaled for this to work. So pairwise distances, calling it with normal candidates, will give us this bunch of numbers here. Okay, so what do these numbers actually mean? So I have here some code that is essentially doing the exact same thing that I did here, pairwise distances on the normal candidates. I'm doing that here. I'm popping that into a pandas data frame just so it looks a little bit nicer. And I'm setting the columns and the index to the candidate names. So here's what we have. This is our pairwise distances in a nice, hopefully nice visual way. And what we can see here is how close they are relative to the other candidates, as well as themselves, which should make some intuitive sense. So if we look at this first candidate, Nizive, compared to Nizive, there is 0 distance. And that should make some intuitive sense. All the numbers in Nizive's row is perfectly the same as Nizive himself or themselves. So there is no distance. They're exactly on top of each other. And you can see that with every candidate, when they look as themselves compared to themselves, there's always going to be 0. So that's a kind of nice check to make sure that this whole thing makes sense and is working. But now we can also look at how the candidates compare to others. So if I look at Nizive, and I look at all the candidates that I see in Bupavel, they are, relatively close. There's a 0.12 difference, so that's in terms of it's all like relative distances. But anyway, it's just the closest one, right? So Nizive would be closest to this candidate. And so you can kind of look at that comparison, but that effectively gives us a starting point for how the voters might look at the candidates as well. We just need to do pairwise distance between the voters and the candidates. So let's do that. Before we go on, I want us to all remember that we can't just pop the voters in because they are not scaled. Everything needs to be on the same scale, right? So I'm going to take our scalar object and do dot transform. I'm going to note here that once our scalar object has been fitted on the candidates, that's our base of reference, we don't want to fit it again. We already have that. We just want to transform. So any kind of new data we come in, we just do dot transform on it. So we have our voters who are untouched. So these should be the same people from before, unscaled. And then when we do the transform, we get the normalized voters. And so norm voters, we can see some values here, and this should maybe look strange, but it should have some intuition as well. So if we look at some of the values here, like this first person, 0.9 makes sense, but you see here this person has a 1.06. But how does that make sense if we have this min-max scaling? Shouldn't the min and max be 0 and 1? The answer is yes, it is, but remember what our point of reference was. We had the candidates, and so those candidates had a min and max that are maybe not as extreme as the values that the voters have. And so what we're seeing here is just this voter had a value that's larger than the max that we saw from the candidates. And that's okay, because this is, again, it's all relative anyway, so it's fine to have this. We'll see some numbers larger than 1, but it's okay because everything's scaled appropriately, so we can actually still do a comparison with these numbers. Okay, so let's take our pairwise distance function, which is what that is, and we're able to actually give it 2 matrices or tables, and they have to all be normalized, of course, in the same way. And so we have our norm voters and our norm candidates. We pop that in, and we're actually able to see the way the voters look at the candidates. So let's check that out. Okay, so that seems like a lot here. I definitely want to go through this, but you can see how each voter, each row, has 5 values that it has, because it's 5 candidates that it's looking at. So each row, there are going to be 100 rows, but only 5 columns for this, because you're only looking at 5 candidates. Okay, so one thing I'm also going to do is just kind of visualize this in a nicer way. What are we looking at? Let's put this into a nice pandas table so it makes sense. I have our distances that we just calculated. I'm going to modify the columns and indices so that the names line up nicely, and I'm going to just look at the first 5 just to see what's going on. All right, so here we have, again, each row is now a voter, and each column is referring to how close that voter is to that candidate. And so we can see here that Tigo, the first voter, is not very close to many of those, but the closest one it is close to is the buy candidate. And so that would be probably who they vote for. So now what we have here is a method of matching a voter to a candidate. What we need to do now is figure out how to pull out this lowest value and associate it with the candidate that each voter wants. Okay, so the way we're going to do this is actually another sklearn function that's very similar to pairwise distances. It's essentially set up for this kind of problem, which is a very common one. And we're going to be using this thing called pairwise distances argmin, and that will basically pull out the information that we want. What it's going to do is it's going to, for each value, it's going to grab the lowest value, but it's also going to give you the index. So for example, with our first person, Tigo, the index that we're looking for is the fourth one, 0 up to 4. So the fourth value is what we're looking for, or the index of 4 is what we're looking for. So I just imported the function here, and what we're doing is we're popping in the same stuff, norm voters and norm candidates, and it's going to do basically the same thing. I'm going to show you the output here. It's a tuple basically of 2 values. It's a tuple of 2 arrays. The first array is the index. So like our first person you see has the number 4 because that's our 4 index. The second person should have this one as the lowest value, which is index 3. And we see that right here, it's index 3. So that's working as expected. And the second array basically shows you the same thing, except it just shows you the literal value, which we don't really care about. We just want the lowest one. So I'm not going to really care about that. I'm going to pull out the first array, which is what that is. And that's what I want to work with. So what we can do is we can pop that as an index to our candidates index and just like get all the names essentially, and get the votes. So this is not the most necessary stuff, but I kind of like the idea of having an actual name so we can kind of see it, just for visual purposes. And so I'm going to grab candidates.index and then index using our array, and that will grab the name based on the index essentially. So if I run that, we see all the names for each person. So this should be a list of 100 people, and their vote that they want basically. So the first person wants to vote for buy, the second for yo, and everything after that, of course. All right, so now we have all the information we need. All we have to do is do our plurality vote, our typical one person gets voted and the one with the most wins. So this is a pretty simple algorithm. I'll go through it real quick. I have this thing called plurality vote. It takes the votes, which is this list essentially of names, and I create a dictionary. I have a max count of 0 and a winner set to none at this point. And I just loop through each vote. For candidate in votes, I check to see if that person exists in our candidates dictionary. If they don't, I set that to 0. This is essentially the count of how many times that person has been voted for. And then I increment that by 1. And then I can check, oh, okay, is this value that has now been incremented, are you greater than the max count, the current max count? And if you are, then guess what? You're a current winner at that point. And we can set the max count now to that new value as the value. And the winner is now that candidate. Again, at this point, so we keep running through the list. And at the very end of it, we will have an updated max count as well as a winner. And what we care about is just the winner. So here I have a F string that just returns the winner and then their name that's capitalized. So if I instantiate this and I can now call this, we can see who wins. And hey, the winner is Roe Doe. Roe Doe. Good for them. Yeah, so that's nice. I think it's also cool to have some visualization. So I'm going to actually make a quick graph of like who won and by how much. And we see here that Roe Doe, that's a weird name, won by quite a lot. They won with like I think over 45. Okay, so that's interesting. Now we have actually, I know it took a while, but we basically have the foundation for how we can get our ranked choice voting working. Everything is there. We can generate people, we know how to compare them, and we can generate, you know, plots and things. So everything's kind of set up. We just need to kind of discuss this algorithm. How does ranked choice voting work? The idea is actually fairly simple. Basically, voters actually just rank their candidates that they want in order. And so you can actually vote for any number of people. I think most systems allow for a certain max cap. So if there are like 10 candidates, you only get to pick like 3 or 4 or something like that. But anyway, so you basically rank the people you want to vote for, and then you go through successive rounds. So the first round that happens, the first person everyone voted for gets their vote. And you make a basic check. So if someone has over 50%, then they just straight up win at that point. So that's, you know, fairly straightforward. That would be akin to the plurality voting system. But if someone doesn't have that majority vote, then we eliminate the person with the lowest vote. So imagine that Bupe Vale here has the lowest vote. Those people who voted for Bupe Vale, their vote now counts toward the second person on their list. And then the next round goes, and it just counts up again. Basically, it counts up. Okay, who has the most votes at that point? With Bupe Vale having been eliminated, so you repeat the rounds until a winner is determined, and that is it. So in order to simulate this as best as possible, I want to consider our 5 candidates, but I want to actually limit the votes from to give a max of 3. So I'm going to say there's a max of 3 candidates that you can vote for. You have to rank them. But you can imagine that, again, as realistically as I can simulate this, you would imagine that some people only vote for 2 people, and some people only vote for that one because they're still stuck in the plurality system, right? So I want to simulate the fact that people may choose between 1, 2, or 3 candidates in their ranked choice. Also, you have to recognize now that instead of a single list of single votes, we're going to want a nested list where each voter will have a list of ranked votes. That information that we still need is in that voter candidate distance variable. So if I check out that variable, I'll kind of show you what I mean. So this list here, it has the candidates ranked for each voter. That's basically it. You know, we just need to pull out who are the top 3 for each voter, and then some people might pick 3 or 2 or 1 from that. So that's all we have to kind of figure out. So we can actually use another arg-sort method from NumPy to get the indices that would sort a given array. Let's check that out. So here I'm going to grab our first voter, which doesn't exist because I need to run all above. All right, folks, just as a heads up, I had to reload this document, and that required basically resetting some of the randomness that went into creating it the first time. So you'll see here that like the candidates have different names and there were some different values. Our first voter here, which I'm grabbing, had some different values that you are not used to, but just keep in mind, it's okay. The code is still there. It's just an issue of just I had to rerun the document. Anyway, so we see here that if we look at our new first voter, they have a value here that's less, the smallest one here. And so we would want to figure out how to rank these numbers. So if I do np.arg-sort and I put in our first voter, it's going to tell us which index should come first. So 1 is referring to this value here. That's the 1 index. Then the 4, that means 0, 1, 2, 3, 4. That means this is the next lowest number. So these are the indices that would sort this array in the proper order. I'm going to define a variable here, which is our first voter sorting array. And I'm now going to take our first voter and then index using it. And we see those values using this index is 1, 4, 3, 2, 0 will give us all the values in sorted order. What we can also do is look at what these indices are really referring to, which are the candidates. So if I have our candidates, so if I look at the candidate names, which is at candidates.index, and I put that array in there, we actually get the names of the candidates. Remember, these names are a little different just because I had to reset. So this is exactly what we can use on each voter to figure out who they are going to vote for. The next thing I want to do is figure out how to randomly select between 1, 2, and 3 of those top votes. And the thing is, I don't want them to be in the same proportion. I'm going to simulate this to assume that most people are going to pick 3. And some small percentage are going to pick 2, and very few people are going to just only select 1. So what we can do is actually use NumPy's random.choice method, which is going to allow us to put in a list, and it will select those items typically at random, but we can also tell it what probabilities we want to select at. So for example, if we put in p equals 0.1, 0.3, and 0.6, that's referring to the probability of getting a 1 at 0.1, and then 2 has a 30% chance, and 3 has the largest chance of 60% of these 3. So if I run this a few times, we'll mostly get 3s and very few 1s and 30% of the chance getting 2s. So that's what we can use for that. So what we can do then is take our candidates, which our first voter has. I'm going to use the sorting array from that. I'm going to grab the names of the candidates in all first ranked votes, which looks just like this one up here, basically. Then I'm going to grab a max vote index, which is either a 1, 2, or 3, using our np.random.choice, which is going to grab one of these values in these proportions, and it could be a 1 or 2 or 3, but we don't know. And we're going to say, okay, we're going to take all of our first ranked votes, and we're going to index using up to that amount. So if this is a 1, it's going to grab just the first value. All right, so it looks like we got 3, which is not that surprising. Let's try again. Here we got 2, and once in a blue moon we'll get a 1, and that's basically what we'll see here. All right, so if you know who you're talking to, we like to do things abstractly. So what I'm going to do is grab all this logic that we were talking about and put it into a function so that we can just iterate over each row to do that. So here I have a function. It will take a single row of data. It'll do the numpy.argsort to figure out what are the indices that would sort that list. And then we're going to grab the candidate names using that sorting array. So here the all ranked votes is just the full list of the candidates ranked, but we know we don't want all of them. We might want 1, 2, or 3, and so we use numpy random choice using these proportions that we set up earlier, and we will return the votes with the index determining how long that is going to be. So if we run that and try it out on our first voter, let's see who we get. We get the first 3. Fantastic. All right, so let's apply this exact same logic now just to all the voters. So I'm going to look at my voter canned distances, which is the thing that has all the information that we already kind of set up, and I'm going to do a list comprehension on it. So for row in this, I'm going to call my function and put in the row, and so it looks like this. So one thing to note is that this whole thing is going to return a list, but each item of that list is technically a numpy array, or in this case an index. What I want to do is just convert that inner thing to a list because I want to make my life a little easier. So I'm going to call .toList on that numpy array, which converts into an actual list that is a little bit easier to reason about. Okay, so I just put a little comment here and then just store that as a variable, and we can look at the top 10 votes, and that's what we get. So right now we have all of the voters as a list, and each voter has a inner list that refers to who they want to vote for in the order that they want to vote for that person. So this has everything we need for our ranked choice voting algorithm. But what is the algorithm? Okay, so here is the ranked choice voting algorithm that I set up. It may not be perfect, but it works. Okay, so what I've done here is I'm importing the math library as well as the deep copy function from the copy library. Then I'm defining our function here, which will take ranked votes, which is essentially just our list of votes from each voter. I'm going to have verbose equals false. This is just so I can keep track of things while the algorithm is running. I'm going to overwrite our ranked votes with a deep copy of our ranked votes. That way I'm not messing with the original. I will be doing some modifications to the inner list when I eliminate candidates, so that allows me to keep track of that without modifying the original. Then I have a set called eliminated. Then we have a dictionary of candidates. This is just a dictionary that will be actually renewed every time we have a successive round. This is going to be used to count the votes for each candidate, but each new round will have to kind of reset that. For our result history, this is just a list, and what I'll be doing is after each round, I want to keep track of what each candidate got in terms of the votes. So this is actually going to be something I want to return just to kind of have a running history of each round, what happened. And then I want to establish what the winning count is. So the winning count is essentially the threshold that you need to pass in order to win. That is going to be the length of the voters, which should be 100 at this point. Divide that by 2 and then do math.ceil. Then we are looking at a function here called winner found. This is just a little helper function to allow us to determine if we have a winner. There's a base case here because sometimes you might have all the people eliminated except for one, and that last person should still win because there's no more competition for that person, so they got the most votes even though it wasn't technically 50%. This is allowing us to prevent our while loop from running forever, essentially. So in our list comprehension, we're looking for count in candidates.values. Candidates is a dictionary that is going to have a running count for each candidate being the key and the value being the running count of how many votes they get. And so we're just checking, okay, how many votes does each candidate have, and does any one of those candidates have a vote count that is over the winning threshold? If there are, then that person wins, and we found a winner. So this should return a list of true and falses. If there's any single one that's true, then we are going to also return true. Otherwise false. Here I have a round I, which is just the iterator for how many rounds we're in. We're going to run a while loop while there is no winner. the winner has not been found, we're going to increment our round count to by 1. And then if we have a verbose setting of true, then we're going to just print this F string. Hey, we're starting the round, whatever it is. And the winning count, just as a reminder, is of this value, which won't be changing, but that's nice to have. We're going to reset our candidates dictionary. Again, each round we want to reset that. And then we're going to start the round. So what we do is for each voter, we're going to say for ranked vote in ranked votes. So remember, ranked vote is now a list that each candidate has for their ranked vote. So that's going to be something like this. And so what we do is we're going to check if the length of that exists at all. If a particular voter voted for only people who have been eliminated, then their inner list will be popped essentially. So it'll be a length 0. We want to kind of skip those votes. Essentially, that person doesn't have their vote counted because they've only voted for people who have been eliminated. And so that's one check there. And then we'll see, okay, while the length of that exists, and so if that ranked vote first person, that means that's the top of their list, is in the eliminated set, which is up here, a running set of those who have been eliminated, we want to pop off that first person because they've been eliminated, so we don't want to be considering them. So we're going to keep popping from that ranked vote list until this is false or until it's basically empty. We do another check. So now that I think about it, I actually don't need to do this. This is the same code here and here. So I don't think I need to check that length twice. I think I can actually remove that. So this will be false if it's false to begin with, and it's going to stop this while loop, and then it will check here and we'll do continue. So I think actually this is a better code. If we've basically eliminated all candidates from that particular voter, then we can just continue and just ignore that person because they don't have anyone to consider. Otherwise they do, and we can grab who their top pick is by grabbing the first person in that inner list, and then just check, okay, if the top pick is not in candidates, that means during this particular round we haven't seen this candidate being voted for yet, so we just need to add them to our empty dictionary. That's all that's doing. And so it's just setting that person to 0, and then we're going to increment that count by 1. This allows us to go through each ranked vote, grab who their top candidate is if it exists at all. Otherwise we just ignore that voter because we've eliminated all considerations, and then we just tally up how many votes each candidate has here. And if we're verbose, then we just I want to print out the candidates at that point. It's just a dictionary, that's all. And then I want to also take our result history and append our candidates as well. This allows us to keep track of like what each candidate got for each round. And here we can now check if there is no winner, then we basically need to eliminate our last candidate. And so this is the logic to eliminate the last candidate. I want to set last candidate to none at this point. I'm going to set the lowest count as an arbitrarily large number, infinity, numpy.infinity. We can easily beat that when we do our check. And then I just go through candidates.items and I just check, okay, if the count is less than the lowest count, at the first time it's going to be infinity, so it's easy to beat. The lowest count is set to that count, and the last candidate is set to that candidate. This is similar to how we did the plurality vote, except now it's kind of like inverted because we want to eliminate the lowest person from that. So that's basically all we're doing here, and at the end we will have determined who the last candidate is, and then we're going to add them to our eliminated set. Verbose being true, we're going to print out, hey, here's who got eliminated. Okay, so at the end of all this, that means this while loop has ended, which means that we have found a winner. Either there's a winner who has a count that's greater than the winning count, or there's no one left, and so we just return true for that last one person. Either way, we now need to figure out who the winner is. And so we basically do the same thing that we did up here for eliminating the person. Now we just do it in reverse. We have a top candidate as none, a max count as negative infinity, an arbitrarily small number, I should say here. And then we just deconstruct our candidates.items. We look for the max count. We set it here along with the top candidate. And once we're done with that, we will have determined who the winner is for sure because they have had the max count at that point. And then we return that top candidate, the winner, as well as our result history. That's a lot. That's a mouthful. It's much more complicated than the plurality vote for sure. So let's use our function here. I have ranked choice vote with our ranked choice votes, which is that list. And I'm going to set verbose to true, and let's see who wins. Okay, so start of round 1. Winning count is 50. That's not really changing. And here are the candidate counts. We have Simagul at 41. Simagul doesn't have 50 basically. So we eliminate Haksujo, which has the smallest count. And once they're eliminated, then we do another round, and you'll see that some of the counts change, right? So this person who actually gained 3 votes. 3 of these people voted for Hak Suju, but had Who as their second choice. Candidate Wallo Hido had 12 and it went up to 13. So that means one of the people who voted for this one went to them. We have Simagol with 41 still, not enough, and so we eliminate Va, and that's what we see here. Oh, this is interesting. Oh, you know what? This is interesting because what we have here is kind of a tie for who gets eliminated. So it picked Walahido. I'm not sure like what's the tiebreaker here, right? So I'm not quite sure what happens there. I'm gonna look that up actually. I'm looking up the Wikipedia instant runoff voting, which is another name for ranked choice voting. If there is an exact tie for last place, there are various tie-breaking rules, one of which is to basically look at how many one candidate got in terms of like first order votes. So you might imagine, if I go back here, like Walahido, they had 12 votes to begin with, but because Haksaju got eliminated, they then gained 1 vote. But Va had 13 to begin with. So in terms of like quality votes, Va should be kept. You know, we should eliminate Walahido because they had 12 first order votes and then 1 second order vote. So it actually kind of worked out that Walahido got eliminated in this situation, but my code does not allow for that. All right, here. So I'm going to put that at the bottom of my code here, that this code does not allow for elimination ties. Check out the Wikipedia. We now have these people. Va got eliminated. Great. And then once Va got eliminated, we then have only 2 candidates, and Simagol got 56, and therefore they win. We don't need to keep counting. Folks, we did it. Woo! We have ranked choice voting simulated. All right, cool. So I'm really excited because this really makes sense, and I'm glad it's working out. What's cool also is that we can modify this any way we want, right? So we can set 100 candidates or 10,000 voters. We can alter their features as well. I thought that was actually an interesting point, that some of these features, and I'll dig into this a little bit more right now with some visualization. We can dig into like what features were some candidates getting voted for and why. Okay, so I'm always a big fan of visualization. There's a lot that goes into making good visuals in Jupyter Notebook or Python at all. I'm using Seaborn, Matplotlib, and it goes beyond the scope of this particular video on like how all this stuff works. You'll have the code here. I definitely recommend looking into the documentation on this stuff. What we have here is the ranked choice voting by round, so round 1, 2, 3, and 4, and we can see how many votes each person got and kind of see what's going on here. So we can see that Simagol kind of had the lead to begin with and just maintain the lead all the way through. What we could also do is look at the candidates themselves and kind of see, okay, this is the data here. The question is, what did Simagol have going for them that made them such an appealing person? And so we see here that their love of cats was pretty low. That's a shame to see, but they didn't like cats too much. Income, though, you can see here that the income could be a serious factor here. And what we can look at then is also the voters. So let me check out the voters, and I want to actually look at the voters summary statistics, which we can do with describe, and we can see here what some summary statistics are for the voters. So we can see a count of 100, of course, so that's great. A mean of 69,000 basically. We can also look at the quartile, which is, look at that, look at the quartile, like basically smack dab right there. 56,000 is what about 50% of people had. And what do you know, Simagol was right around there. All the other candidates, if you look at the income, they were fairly high, which is, I guess, not that unusual for some voting areas, but it's interesting that I think that might have been the thing that brought this particular candidate that many votes. They were just so in line with what most people had. So I'm gonna wrap this up. I just want to give you some next steps of what you can actually do with this stuff. You'll have the code. I'm gonna put all this stuff on a repo so you can try this out. What you can try is alternating the number of candidates, voters. You add more dimensions, make them more complex. Like the income, for example, I was pulling from a gamma distribution, but you can try all other kinds of different distributions, and you can use qualitative data, for example, so you can use categorical data. You'll have to kind of figure out how to turn those into numbers because everything needs to be math in the end, but you can certainly do that. And you can, of course, try all different kinds of visualizations. I love making data visual, and you can do so many cool things with it. So that was my next take on I Can Code That, and I hope you enjoy the series, folks. If this is the kind of content you like, make sure to like, subscribe, do all the good things, and I will see you next time.